Okay. So my name is Poting Ling. Now is my time to share my personal experience in soft robotics. Before I start, I will show you a picture taken 10 years ago. It's a picture of myself, which doesn't look like me uh, when I got married. Probably the best picture I have taken in my whole life. So I never change it. I went to a graduate school called Rutgers in USA, New Jersey, back in 2004. I got actually master. It's a typo. I got my master and PhD in Rutgers, and also work as a postdoc in Rutgers. Just like Professor just mentioned, he also got his degree in USA. Then I came back to Taiwan to teach as an assistant professor in a private university called Zhongyuan. In 2017, I started my job in Taiwan Tech. So now I am a full professor. In 2021, I became the director of IITP and GDEP from 2022. Actually, my promotion to professor was very successful because the dean wanted me to serve as a director. So they approved my promotion with smiles. Then I become the director. In exchange, I serve for the School of Engineering. So last year, I became the director for Robotics Center because the senior professor is retiring. Okay, so in the past, when I was a PhD student, I work on optimization. It's more related to mathematics, statistics, very theoretical research. But when I came back to Taiwan, I realized we need to apply those theory to practical applications. So robotics is one thing I applied. I think I can skip this part. I mentioned about how many projects, papers I had. It's not necessary. So, what is soft robot? So, in the definition of Wikipedia, so over here there are some keywords. The robots, if it's composed of compliant materials, so it's not rigid. If a material is flexible, soft, compliant, then you can say it's a soft robot. So, what's the difference between a soft robot and a rigid robot? There are some important purpose. Usually, for soft robots, we want more safety for the robot because rigid ones they are very strong, they are powerful, but when it hits a wall or hits a person, the wall is damaged or the person is dead, right? But if it's a soft one, maybe it's safer. So I recently, researchers around the world they try to develop new soft robots, not only in mechanical field, they also get researcher in the material field because we need soft materials. Mechanical engineers do not know how to make soft materials. We sometimes need softer materials, sometimes we need functional materials. So that's why we use this idea in this program. We want the mechanical engineers works with material science engineers. So you can see from this trend of the development of soft robots from the early 2000, there's not many research papers, not so many, but in probably 5 or within 10 years, there's a huge growth of soft robots. Now, if you later on study for graduate research, for master. And if your professor is a professor in robotics, probably he is working on soft robots because it's easier to publish recently. People care more about soft robots nowadays. Almost, I cannot say a lot of rigid robot research was done. There's nothing more to work on. So people now shift to soft robots. There are still a lot of problems to solve. So I believe if you learn something in these 2 weeks, in the future you can also think about working on in this field. This is a very hot topic. Okay, so there is even a new journal. So for professors, we need to write research papers, publish in a journal. There's a journal even called Soft Robots, Soft Robotics. So what does impact factor mean? Every article, every year will be cited by how many other journals averagely. So every article inside this journal will be cited by other journals for around 8 times. So there's a 8 times impact to the world. In robotics field, this is very high, almost like a top 10% ranking in robotics. So just to let you know, in the past it was not that hot, but nowadays it's very hot. Okay. So I dissect soft robots into many different categories. We can take a look at each one of them. Let's start from the upper right corner. So if you want to make something soft, you need to worry about the materials. Like some of the materials are listed here. PDMS is a very friendly material. I think we will use it. Do we? No, we don't use PDMS this time. But in many research, people use a polymer called PDMS. It's a kind of like a glue, and there are two bottles, and there's a specific ratio. When you mix them together, it will be solidified. So originally, it's like a glue shape, like liquid, but with some viscosity. You can easily pour PDMS, uncured PDMS, in any container, and once it's cured, becomes solid, then you can shape it. So this kind of technique is like a molding technique. Also, EcoFlex is another kind of polymer. It's very soft, softer than PDMS, and also silicon rubber. Or nowadays, you can even print soft materials such as TPU and some other materials. So in this summer course, we will be using a kind of silicon rubber. It's called silk skin. Silk skin. Okay, so it's a 1-to-1 ratio liquid combined together. You will have some time to before it's cured. So we will use the molding technique. On the first couple of days, you will make some mechanical design. Actually, you will design the mold. Later on, when we work with the material, you pour the uh, silicon rubber inside the mold and then release the mold. You can have the soft structure. Okay, the second important idea for soft robot design is to have some kind of concept. So you even can combine materials in different strength. You can have weaker parts, you can have stronger parts. So when there's a force applied to the structure, the weaker parts will deform. When it deforms, the entire shape of the soft robot changes. So if you can design the arrangement of the material in a smart way, maybe you can bend a finger or move an arm, something like that. So it really strongly depends on good ideas. Maybe there are some ideas has never been thought of. And once you get to know soft robots, you can put crazy ideas in those. And uh, and also for the structural design, you can, like I said, you can have composite. Composite means you can mix different materials with different properties, or you can even try origami. Did you see the earlier presentation when Professor Sakamoto showed his satellite? There is the solar panel. It was folded at the beginning, and he tested how to unfold the solar panel. It's the trick of origami. So origami is, I think for Japanese, it's a very simple word, but for Taiwanese, probably you don't know. Origami is like 折纸艺术, folding papers, the art of folding papers. So there are even researchers like Professor Sakamoto spend some time to study how you can fold flat structures. And once you release it, it become a larger structure. Okay, so there are even researchers working on soft design with origami. Okay, so how to make it? Like I said, molding technique. Soft lithography is a semiconductor uh, microfabrication process. In this course, we will not use soft lithography. So it's similar to molding, but usually in a very small scale. You can have a mold with microstructure, and then you put your material on top. So it's like a imprinting to the structure based on that microstructure. And like I said, we can try 3D printing. So usually when you have a design, you need to think about where you are going to apply soft robots. Over here, I mentioned several applications like a soft gripper, robot legs, or what is an actuator? Actuator is a device that will be have some motion after you apply some kind of energy, like electricity, pressure, or some kind of power. Then the structure deforms in a certain way, and it can perform some action. Or you can even use soft material as a sensor, as a valve, micro valve, or have biomedical applications. So on the left hand side, let me go through this. Usually, you need to control the robot, and there's a knowledge of kinematics. So kinematics is a knowledge about motion. In the past, usually we learn about rigid body motion. So we have a bunch of rigid structure connected together. When you apply a force or some kind of actuation, those rigid body deforms, change its coordinate. But for soft ones, it's much more different. So there even is a study for controlling soft robots. So what is a forward and backward? So let's say my arm is a soft arm. If I want to control my shoulder, my elbow, I control the angles, then I can decide where does my fingertip goes. By changing my shoulder angle, the position of the fingertips changes. So when I control my arm, I control the angles of the joints. So in the end, I can reach my fingertip to a certain point. So that kind of way, by controlling your variable and reach certain goal, you can say it's a forward study, forward kinematics. How about backwards kinematics. Backward is like a mission oriented. You want your fingertip to reach a certain point. You don't care what's the joint. You just want to complete this mission. So you backwardly compute what will be the proper angle for this mission. So it's a mathematically it's a forward calculation or backward calculation. So in soft robotics, you also need to worry about how to control. And for the deformation type, I show three different types. Linear motion, so something moves along a line. Bending motion, some kind of rotation. Or twisting, right? It's possible to have actuation to allow your soft robot to move in different ways, but you need to think about how to achieve it. Models, usually you need some math. Once you actuate, you will generate deformation. So you have movement, or you can generate some force. Do you need to care about how much deformation it makes or how much forces it's gonna generate? So in our topic, we are going to build some kind of robot arm, something like an arm. You need to think about how you can deform more or less. You can generate more force or less. So that would be something you need to work on. Bonding is a very important issue in soft robotics. Usually for soft robots, they are made of soft materials like polymers. And once they are cured, they have usually they have poor surface property with surface contact property with other materials, which means you usually cannot find a good uh, uh, like a glue between two kinds of materials. It's sometimes very hard. For example, PDMS, the surface energy of the polymer is quite low. So if you try to glue a piece of PDMS onto a piece of metal, sometimes it's very hard. But for material parts, like two pieces of metal, you can just drill a hole, use the bolt and nuts and bolt to tighten it. But for soft ones, how can you do it? When you drill a hole to the soft material, it may break. Or when you mold the structure with a hole, when you try to tighten the soft material by bolt and nuts, it's very hard. It may break the structure. So bonding is always an issue. For later on, I will introduce something called plasma bonding. So plasma sometimes will change the surface energy of polymer, allowing polymers to be able to glue with each other to create some kind of bonding between them. Okay, so what would be the usual actuation types? Pneumatic means high pressure. Usually pumping some pressure inside a chamber, blowing some kind of bubble. Because of the growth of the bubble, that will deform your soft structure. Or by a cable, apply a cable and just pull the cable. Or just motors. Okay, maybe the motors will drive some part. I will introduce those in my today's lecture. Okay, so over here, there are some popular soft materials. PVDF is a pretty common, very famous one nowadays. It's a kind of piezoelectric material. PZT also piezoelectric, and shape memory alloy. There are metal types and some other types. Carbon nanotube, very hard but very small. Over here, also, there are some shape memory polymer as well. Elastomers, soft ones. So in this map, you can see we try to have softer. We can design the softness of the structure by choosing a proper material. And each material has its limitation. its softness is within a range. So maybe you need to know about the material in advance. And once you choose a material, it can only achieve certain goals. It cannot be softer or harder. And also, if you from this map, if it can carry greater stress, usually it's a stronger material. Okay, so there are some references on the internet you can go check out. Now, some more examples, and also help you to know about the difference between how you drive the soft robots. These two examples are the cable ones and the pneumatic ones. In this first particular design, this researcher used three different motors to drive the cables, and the cables were penetrating through the structure. So the structure has a hydrogel body, so it's a flat. It has a soft body inside, and at the tip, uh, the cables were tightened at the tip. So once you pull, you shorten the length of the cable inside the body, so certain part uh, will be compressed because you apply different amount of forces at different parts of the cable. Then you generate a different pulling force inside the body, allowing the entire body to bend towards certain direction. Right. So that's a really interesting idea by combining soft structure and also cables. This is a different example using air pressure. So this is like an illustration of the soft robot where you will see different areas of air chambers, like air bubbles. And you can have pressure control for each one of them by turning on or off, or enlarge or decrease the pressure at different channel. You can allow different deformation here and there. So because of the deformation, this whole soft body will be changing its shape by the deformation. But usually for both of these two kinds of soft robots, the deformation is very nonlinear. What do you mean by nonlinear? Usually for rigid structure, if you enlarge the power, the motion will linearly increase. So that means the relationship is linear. But for soft ones, sometimes when you increase the pressure, it doesn't deform at the beginning. Once the pressure reach up to a certain level, the soft matter starts to deform. So the structure dramatically deforms. So from there, you can tell the way to control the soft robot is more difficult because it's not linear. The relationship sometimes is not linear. So that's why people are working on soft robots right now. Let's talk about the functions. If we have um, soft robots, um, are they strong enough? Can they help us carry heavy objects? And how often do we use it? Because for rigid structure, the more you can have thousands of motions repeatedly without breaking. But for soft ones, soft material may have an issue of fatigue if you deform too many times. Think about rubber band. If you pull the rubber band multiple times, there's heat generated inside the rubber band, and also the heat will weaken the material property. One and for just several times, maybe the rubber band will break. Even though rubber band has a good potential of large deformation. Usually, rigid body doesn't have large deformation unless you build a large one. But the what's interesting about soft material is that you can elongate its size. but it can break. So you also need to think about your mechanical design. Do you need the structure to be strong enough, or do you need the structure to be able to deform for a lot of times? Okay, so those are the things you need to think about. And also, for different applications, they need special need. They have special needs, and researchers try to learn from human nature. So over here, the biocompatibility, because one research field is try to incorporate soft robots inside human body because they are soft, so they can be embedded inside animals or humans' body, like an artificial organ or surgical devices. But if you try to put something in your body, you want those materials to be compatible to your to human, right? So designing a soft robot is not that easy. It's not like you only need to worry about strength, fatigue, shape, deform, control. Not only those, you also need to think about when you use it. Do you need to worry about the environment? If you put it inside your body, then does it harm a human's body, right? And also, sometimes we build soft robots to mimic the nature. So let's say artificial heart. You want this deformation to mimic the motion of the real heart, right? So that you want this mimicking to be as realistic as possible, something like that. So these researchers show a map of some of the well-known devices and show the level of biomimicry and also biocompatibility in this map. I believe there will be more applications in this matrix in the future. Okay, now in the history, there's already a lot of soft robots has been made. So in this paper back in 2016, the researchers show a list of soft robots. And from here, you can see a difference between this lineup. On the left, they are also soft robots, but they are stiffer, basically more rigid parts. On the one in the very right, it's completely soft. It's like an octopus made of PDMS. Inside the octopus, they have chemical compounds with microfluidic system, so microchannels. So those chemical compounds will flow through the channel and then start to mix and have chemical reactions. Because of the chemical reaction, some gas will be generated. So some channel inside the octopus will be enlarged when the gas generated. So they use this kind of way to control the legs of the octopus. So very smart design. So over here, uh, you can also learn from researchers. Read more papers in the following days. Try to have, if you don't know how to start, learn from what has been done. Maybe there's a design that has been done in a different field, but maybe one of the key idea can be implemented in your own design. We will show you what we have built for the project, but that's not the only way. You are allowed to make your own design. We will be here to help you, but not say no to your design. You are free to be crazy. Okay, so this is very similar to what we are trying to build for this year. Wearable soft robots, and mostly for the middle one and the right one. sometimes people build this kind of soft glove for rehabilitation to help patients to actuate their fingers. Sometimes they have difficulty bending their fingers, so they need to rehabilitate their fingers. So the goal of this year's topic is to build this kind of soft glove, and we will use pressure to control how much bending you create. This is one solution. You can have new solutions. More details will be given later on by the TA. Now, focusing on the pneumatic actuator, usually we try to have air channels inside soft materials. But think about this. Soft materials usually are polymers. So before it's cured, they are liquid phase. So like a glue, right? You have a bottle of glue. If you pour the glue inside a container or just pour on the table, certain time later, that portion of the glue will be solidified, become solid. But there's no channel inside. So just a piece of soft matter without any functional channel inside. So the importance for pneumatic actuator is that you need to generate air channels inside. So how do you generate air channels? Maybe you can have a container and you can put something inside to to block some area of the material. Once it's cured, take away what's inside. Then you have an air channel. Maybe that's a good way. But if the channel is very complex, in a very complex shape, you cannot take it out. Then what do you do? So usually in the field of soft robotics made of polymers, they try to think of crazy ideas for having air channels inside the soft material. Like in this left example, they have one mold. For the first mold, it's looking like this. Let me draw. For the first mold, they pour polymer inside the mold, and there's some pattern at the bottom. So those patterns are there to generate grooves inside the soft material. So once they release this soft material, there are some holes, there are some grooves inside this piece of structure. Then they just need to find a cover, put them together. Then at the center, you will have an air channel. But when you have the cover, put it on top of the first piece of the soft material, how do you put them together? Do you apply another layer of glue? So that will be the issue of bonding. When you bond two pieces of soft material together, if the bonding strength is too weak, when you apply pressure, it will explode or it will leak. Air will leak. Then it's not working well. So that's why I said at the beginning, you need to think about what kind of material you use, how you design the structure, and how you actuate. Here we use air pressure. How do you bond? Sometimes you need to bond multiple layers. And how do you bond so that it's strong enough? So we need a lot of knowledge of material science. Sometimes mechanical engineers, they can have good designs, but they don't know how you can have good bonding of soft materials. That's why you guys need to work together. My TA are from mechanical engineering department. What they did was read research papers and try to follow. they cannot come up with new ideas of material like a recipe or tricks. You guys probably can do better than them. Okay, now over here on the left hand side is the air channel using the molding technique. And over here on the right hand side, they blow high pressure into the air channel, and you can see deformation, but the deformation is uneven. How come it's uneven? Because when they create the structure, they intentionally generate different thickness on both sides of the channel. So thicker area will be stronger, thinner area will be weaker. When it's deforming, of course, the thinner area, the weaker part will deform more. So that's where your idea can come into a soft robot design. You can have designs in any shape. By the combination of your crazy ideas, you can deform something in a very unique way. Okay. This is a combination of a little bit origami and also pneumatic, I think pneumatic actuation. So they generate this kind of structure, like a folded structure, origami based. And they basically at the end generate something like this. And I think they shape this unique structure by the molding technique. And the molds were made of 3D printing. These materials were made by silicon rubber. Just like what you are going to do for the following weeks. We will use computers to design the mold. We use 3D printing to print out the mold. And then we pour silicon rubber inside. So you can even build something like this if you want. Okay. Over here, you can see they can control how this structure bends. I think by applying different actuations in different channels. And like I said earlier, we need models. We need to know how much deformation it can generate by different ways of actuation. If you cannot control your soft robot properly, then it's just something uncontrolled with your high pressure. So at the end, we must have a good control of our soft robot. And that kind of relationship is not a linear shape. So you need to test your robot by different pressure. Then try to take measurements to figure out, okay, when I apply this amount of pressure, then the bending angle is this. When I increase it, the bending angle is this. And it's not linear for most of the time. Now, once we know the behavior of your soft robot based on the amount of actuation, how do you make this whole thing a complete system? You need the help of computers and electronic device, so-called a mechatronics system. You need to build something like this. Otherwise, you need a human worker to control the pressure valve on the side. We don't want that. We want this whole thing to be automatic, right? So later on, you will be building something like this. You have computers, you have some circuits, you have pressure valves, you have sensors, you have electronic components to get data, get signal, using the signal to control the pressure. So it's going to be very complicated later on, and it could be more and more complicated if you dive deeply into this research field, but it's getting more and more interesting. I hope you can do a lot in the following weeks. Now, here's a practical example. It's mimicking a worm by a smart design in a unique shape. Over here on the right hand side, They are using a kind of special 3D printing system where they cure a layer of the resin and then pour the cured resin up. So at the bottom right here, it's a container of resin uncured. And they have a platform, the black one. It will be attaching to the resin and they will cure the resin at the interface. So there are some part of resin is cured at underneath the black platform. Then they pull up a little bit, cure one more layer, pull up, cure one more layer. So it's a kind of a upside down 3D printing. Once you cure everything, the entire structure will be underneath the black platform. They use this way to cure a design like this. And I think they use a magnetic force. They have magnetic material at the front and the back of this worm. They use magnetic force to drive the worm. And what they wanted to do is to have this and climb into your human body and deliver drugs. That was the idea, but I will be scared about this. Having a magnetic driven soft worm crawling through your body into your lung, maybe deliver some drugs. But maybe one day it's a very well developed. Maybe one day we truly have this kind of medicine. Anyway, here's another example of pneumatic soft robots. This is made of PDMS, and they built many air channels, multiple channels inside the legs. They try different sequence of air actuation. On the right-hand side, you can see they actuate the air channels sequentially to generate a sequential motion of this kind of X-shaped robot. So at the end, it was able to crawl toward a certain direction. Okay. Now, back to what I have learned in the past. This was from my master's degree. When I went to USA in 2004, exactly 20 years ago, I went to USA and my advisor was he just graduated from UCLA and he came to Rutgers, became a assistant professor. I was his first graduate student, and he was in UCLA. He built some kind of micro hand, very small. The size of the hand, the longest distance from one edge to the other edge is only 1 millimeter. Super tiny micro hand. And he claimed it could be used to grasp the fish egg, the small one, not the big one. What's the Japanese name of the small one? I don't remember. Not the salmon fish egg, the small one, like maybe the prawn, shrimp fish egg. No, not the fish. Anyway, the small one. So I forget the Japanese name. When he presented, he mentioned some Japanese name, a kind of a small eggs, like a red color. Sometimes put it on top of sushi or chirashi or whatever. So he claimed his micro hand was able to grasp one fish egg, but it was made by silicon. So the structure of the fingers were silicon, hard material. So to build that soft, it was able to bend. So there are some air bubbles between the silicon. To deform that structure, he worked for so many years to combine soft air bubbles with rigid silicon. Maybe I can show you. I can just Google to show you how it looked like. This one. So the dark structure is actually a very tiny piece of silicon, very tiny. So it was a silicon wafer. The silicon wafer was cut into small pieces, and the transparent part is actually an air bubble. So this was flat. The concept was like this: it was flat, but when you blow the air bubble, because of the deformation, it will bend inward. So that's how he built this kind of soft robot. But at that moment, when he came to Rutgers, he tried to repeat what he has done. But to complete a micro hand like this, it requires a lot of research funding. So we decided to change our direction and try to fully focus on polymer. So that was the time I learned how to work with so-called PDMS. So just like what I have drawn on the board, you can have a mold, you can pour PDMS on top, and because of the structure, you will have you generate some kind of micro pattern on one side of the PDMS. So over here, you can see that's how you can generate air channel. But like I said, you need to bond them together. And we realize we can have bonding if we apply plasma on top of the PDMS. So it's an oxygen plasma, and plasma is a very high power. I don't know how to explain it. It's a high power bombarding the surface of the polymer. So at the end, the surface of the PDMS will have a bunch of OH. I don't even know how to call out the name of OH. So maybe the material science student can help me. So anyway, so kind of like being oxidized. So two layers of PDMS being oxidized, coming together, it will form a kind of bonding. It's a so-called a covalent bond. In Chinese, it's called 共价键, right? So if you have no idea what is covalent bond, for the mechanical engineering students, so it's a O bond, oxygen bond. So the O bond is a very strong bonding, and the rest of the H2O, the water, comes out like vaporized. So if you have done this experiment, you will be very surprised. This kind of bonding happens so fast. Whenever it connects with each other, the covalent bond was formed immediately because the OH property was very unstable, and the covalent bond is a much more stable state. So the surface tend to reach a more stable state. So that's how you can generate bonding. And for the area where you have the hole, because there's no contact, that's why over there's no bonding. So the hole remains there. So at the end, in my master degree, I was trying to measure the bonding strength. So I try different shapes of the bonding, different parameters. And there's a standard bonding test called the blister test, like a test that blows a bubble, a circular bubble. And the purpose is to pump more gas, more pressure. One day it will explode. As it explodes, you can kind of calculate how much bonding force it has. So there is a simple math to represent the force balance at the interface. So it's a very simple model, and I basically generate a through hole at the bottom, and I attached a very thin layer of the PDMS, and then allowing the center area was not bounded. So whenever I blow gas, there will be a circular region that is unbounded. That's my process. I think I can skip this. So at the end, I use something that is very similar to what you are going to do this time. I had air pressure. I have some pressure gauge. At the time I used a circuit system I built by myself. I apply function generator, some function, some signals generated by this device, provided to the circuit system, so it will control my pressure gauge, allowing the pressure to be gradually increasing. And at the time, I also use a LED to show what's the current pressure. So 20 years ago, I used LED, and then I have cameras taking videos, recording the process of explosion. So that was the video. So now you can see the bubble is gradually growing due to the increment of the pressure. At some point, it will explode. So when I was a master's student, I built I don't know how many air bubbles. I have repeated this experiment I don't know how many times. So that was my master's degree, exploding the bubbles. And then I was able to, by the model I generated, I was able to calculate, okay, the oxygen bonding strength between the layers was 100 and something Newton per meter, something like that. Then I know later on in the future how strong my structure is. Okay, and then I try to build something like this. The pneumatic finger. I should not call it micro because it's not even in the micro scale, just a pneumatic finger. So that's what I built. The first one has an air bubble, I think, closer to the top surface. So the bottom layer is thicker. When I blow the air, the membrane on the top deforms more, and more deformation allows pulling force toward up. So the finger bends up. The lower right video shows two channels of air bubbles. So I have one air bubble on the top and one air bubble at the bottom. I sequentially apply pressure to each one of them to allow bidirectional motion. And the left lower corner is to mimic what my advisor has done. So I put multiple air bubbles in this four finger structure, and I blow them at the same time just to see if I can create a micro hand, but in a millimeter scale, not micro scale. Okay, so that's what I have done in master's degree. And then I decided to do mathematics in PhD. I'm not a person who enjoys experiments. Anyway, even I started to work on optimization, mathematical stuff. When I came back to Taiwan, there are still students who enjoys practical applications. So this is the first graduate student in Taiwan Tech who built soft fingers in my lab. And this person used two tricks. One is to combine soft material and strong material. So he tries to have unique shapes of soft materials like this. The blue is the soft one, is PDMS, same material. The yellow are like a rigid structures built by 3D printing. They are there to mimic human bones. Because if you have something stronger over there, then there will be fewer deformation over there. Then you should be able to see finger-like motion. But how do you actuate? So he learned from the literature. He used the cable trick. So he applied a cable through the entire finger, and then there is tighten the cable at the fingertip. So it's a stopper. When you pull the finger, the finger will bend, like the drawing at the lower right corner. So this is how he completed the process. You will be doing very similar stuff for the following days. You need to make some kind of mold. This is what he made. There are some unique designs, and this is where he embed the bone structure into the container. So let me make a drawing. Basically, he had a mold, and he made something like this. And this is where he put PDMS. Okay, so it's like a container and put something like a lollipop, right? So put something at the middle and then pour PDMS, right? Once the PDMS is cured, he will break whatever is holding the bone structure. Just cut it away. Release the finger by opening the mold. So at the end, you will have a structure like this, and he needs to put a cable inside. So he made some tricks. So there is a hole, a through hole, so that he can put the cable through the structure. And like here, over here, did you see? For the bone structure, there's a hole. He used some trick to keep the hole there all the time. And then, so at this stage, he can put a cable through and tighten it. So when you pull the cable, it will bend. Yeah, so that was the design. This is the bone structure. There's a through hole for the cables. And they have like a thin support just for you to insert the bone. Later on, you can cut it. This is what he made. The reason why he colored this into black is because at the beginning it's transparent. PDMS is transparent. So it's hard for you to present this in research paper. So he made it dark. And this is how you put it together as a like a soft finger. And he made a motor. He put a motor right here. He used the motor to pull the cable. By rotating the motor, the cable will be pulled evenly. So the three fingers will be tightened. Okay, that's what he did. And we did this kind of demonstration at some kind of exhibition. I asked him to try this multiple times to see if the microfinger, the soft finger is durable. So for the day, they were giving away gifts inside. How do you call this in Japanese? Like in Taiwan, in Chinese is called 扭蛋, but I don't know what's a. Yeah. So 扭蛋, yes. So at the day, we prepared more than 600 those toys, and people come by. They can push a button, and my students are robot will grasp one toy and then release. So at a day, he gave away hundreds of those to demonstrate the durability of this soft robot. Okay, so that was what we have done in our lab by the first graduate student. And like I said, we need to control it. So not only just demonstrating the motion, right? So this is more mathematical. So you need to know how much cable you need to pull so that you can actuate the finger in a certain level. So he did many analysis. This is more like for a research paper. So he measured the characteristic points on the finger and use a camera to study their positions. So that's what he did. Several models, right? Different models. So at the end, he will be able to build a model for how much pulling force from the motor I can generate how much angular motion. So maybe later on, when you design something for the project, you also need to think about how you control, how much is the control. I have a second student who works on soft robots. I will introduce them in the afternoon. I think it's about the noon time. You guys probably is hungry. So I think right now is a good time to break. I will continue on my slide at around 1 o'clock in the afternoon. So in our campus, we have a cafeteria. So maybe our students or Taiwan, your teammates can show you where you can buy some food. Okay? So before we have the lunch break, any questions? No? Okay. So let's take a break here and then I will see you later at 1 p.m.